Yeah, welcome to the afternoon session. My name is Carsten, and so this afternoon, I think our goal should be that everybody who is sitting here then at the end of the day should be able to set up and run a GROMACS simulation and also run basic analysis tasks and visualize the output and also know where to get help. So maybe I would like to ask you, what is your prior experience with GROMACS? So well, if you say we all work with GROMACS already, we set up our simulations, then we could directly go into the tutorials. Otherwise, if there's people here who say, ooh, I didn't even call any GROMACS tool now, then I will give a very quick introduction, 10, 15 minutes for those. So maybe hands-on who has not done anything in GROMACS. Okay, good, yeah. So let's do the introduction then. So let's do a quick demo of GROMACS simulation setup. After that, we have prepared 3 practicals for today. So one will be, so in the demo, I will just show that. I mean, you can try to do that with me if you like, but let's quickly go through that. And in the practical one with Ole, you will have time to do that all by yourself, and either with the systems that we do in the intro or also with other systems. Ole also brought us a few systems for you to try out. Then maybe after the first practical, we do a very short break of 5 minutes or so, 5 or 10. And then we got 2 other hands-on sessions or tutorials. One is more a deep dive into the analysis of GROMACS trajectories done by Florian. And then there's another one about visualization of MD results done by Jonas. And there you could also just either try to do both or just depending on what you like more, what you are interested in more, pick one of them. I think Jonas also put a GROMACS cheat sheet.
So if someone doesn't have it, you can get it here.
There you will find the most often used GROMACS commands. And of course, during the tutorials, we will be here and we are happy to help with anything that doesn't work as expected. Okay, so what do you do if you, let's assume you have some interesting biomolecular system with a nice question that you think can be answered with an MD simulation, and you want to set up the system and simulate that. So as an example today, we're going to use bacterial protein G and set up the B1 domain of that protein. So usually these colored steps are involved in the simulation setup. So there's a preparation where you think about which input structure you take, typically from the protein data bank. Their questions come, of course, into play, whether the resolution is high enough for simulation or whether everything is resolved. But we're not going to dive deep into that today. We're going to more look at the actual setup for GROMACS, where we're going to use a PDB to GMX tool to transfer the PDB into a format that GROMACS can use to simulate. Then there's this phase where you actually run the simulations, and the third phase, analysis of the results, which we do in the practicals then. So the initial structure of the protein we typically get from the protein data bank. And there we would simply protein G, B1, for example. And this should give us a lot of hits that are related to this protein GB1. And we're going to simply select this one PGB here for today. And for GROMACS, we can just then download a PDB format here. So PDB format. This is what I just downloaded. This contains a at the beginning a lot of text with information on how the structure was resolved and also references where you can read on the experimental procedures. And then what is interesting for us if we want to set up a simulation is, of course, the records that follow here with the atoms sorted into residues here and the atomic positions X, Y, and Z. And you might notice that already here the structure is not complete, so the hydrogen atoms are missing, but that will be taken care of by our PDB2GMX tool later. Yeah. So then let's fire up PDB2GMX. And apart from the hydrogen atoms, of course, PDB2GMX also defines a topology for us. A topology simply is a set of the connections between all the atoms, especially the bonds, which atoms are bonded to each other. And this is information that GROMACS needs for simulation. So the main GROMACS executable is typically called GMX. Can you read that, or is this too small in the back? Still too small or better? Okay-ish? Okay. So I got my PDB structure here. GMX is the main executable. Maybe if you want to get help about GROMACS commands in general, so there's always can call GMX help, either that, then you will get information about what type of help you can call, or also GMX help commands. This will give you a list of commands that GROMACS supports. This is a quite long list here. And if you want to know something special about the specific commands, then you can just put GMX help PDB2GMX, for example. And this will give you the help screen of PDB2GMX with a description, what the tool does. And then I always tend to forget the characters for the input and output files, so that you can also, there's output files specified by these command line switches, and then there's a whole list of other commands that you can use. We're simply going to use a few of them today. We're not going through all of them. So let's do that. PDB2GMX. Input is our PDB file, and the output is let's just call it conf.pdb. Yeah, of course, would be nice to have the GMX in front of that. And then we can select between various force fields. So today we're just going to select the first force field here, and let's also pick the first water model. Typically, you will want to select a model that is suggested, or which you would use with a force field together. Okay. Now we got this topol.top file. And this one, we can take a quick look at that. So this is now a GROMACS topology file where we have now the residues. We see that PDB2GMX added hydrogen atoms. We also see that the charges are there. On top of that, there is now the connectivity defined with bonds. So this is the section where all the bonds are defined, for example. There's also angles defined. And at the end of the topology file, there's a list of, in this case, it just says that there's one molecule of the protein as defined above. And here we also have 24 solvent or water molecules, and these came with the PDB, so these are crystal waters, but we will be adding more waters later. So sometimes we need to edit this molecules section for simulation setup. Okay, let's go on. That we already saw. Okay, now if we would now look at this file, for example with PyMol, then we see it's just there empty in vacuum. And of course we want to define a simulation box and we want to fill in some solvent. So the simulation box we can add with the GMX edit conf. We give it the PDB file that we just got. And we say that we want a distance of 0.7 nanometers to the next, to the box boundary. We're going to use a simple...
Sorry, excuse me, how did you get the PDB again?
Sorry?
The conf.pdb, where did that come from again?
From our last, this was the output from our last command, from the PDB to GMX. Would be one.
You can also look at the cheat sheet, so we go from the PDB input structure, use PDB to GMX, and then this is at a conf.
So this one here. Maybe you call it differently or so.
Yeah, okay, thank you.
Yeah. So this is the PDB with the hydrogens. But I mean, don't worry if it doesn't work everything right now. So there will be time. You can repeat that in the first practical. It's just, yeah.
Excuse me.
Yes.
Is the structure that you download from the PDB bank is completely okay? I mean, there isn't any missing. I mean, because otherwise it would give us error. The PDB GMX, yeah.
Yeah, that often happens, of course. Yeah.
But now it was okay. I mean, for this file.
Here it was okay.
PDB file. Okay.
Yeah. Yeah, there's more details you typically have to take care about. I mean, this is just to get us started.
Yeah, okay. Yeah.
Is it a format that always has to be PDB, or there is other format that can be loaded?
I think usually it's PDB.
Yeah, but it's GMX.
You mean from PDB to GMX or later?
Let's say my coordinate is just like X Cartesian, X, Y, Z, or it has to be in PDB.
Yeah, so you can use any file that the tool supports. This would probably be PDB or GRO, and some other GROMACS. Let's say, which I guess that this is just taking. So these file formats are possible, so simple text file won't do it. So you would have to manually probably get that in PDB shape or so.
Okay. And the following question is, what happens if, let's say, there is some atoms or indexes in our PDB file that couldn't recognize this, the force field that we choose?
Yeah.
What should we do then if that thing happens?
Yeah, I mean that. Yeah, you often have stuff like that, and I think you will need special treatment there. So maybe let's postpone that for later. Just for now, that we get a quick walkthrough. I mean, there's admittedly there's a lot of stuff that can also go wrong with getting the PDB and setting up the simulation, and oftentimes it won't work as smoothly as we see it here. But
go to the sharing desk.
Okay, we already called it Jonas edit code. Okay, now we define our box.
Is it this one? Let's try it. Okay, just type in along.
0.7 nanometers distance, box by cubic.
Info mode.
Okay.
switch.
No, where's my mouse? Okay. Now there should be a box here. And now let's fill in a bit of water. Try to make that visible here. So this we do with GMX Solvate. We give it our PDB file with the box around. And with a CS switch, we simply choose a box with already, this is a box with 200 simple water molecules in it, and this will simply be, let's say, stamped over our box, and where we have clashes, the waters will simply be taken out. So it's like everywhere where there's volume, the water molecules from this SPC water box will be put. And we also give it the topology file simply because the tool will also add the water molecules to our topology. Yeah. And now let's call the output water.pdb. And if I now look at the end of the topology file, then we see that the tool has added 4,000 water molecules for us. And the whole system looks now like this. And we see that this is not real water, so it looks a bit crystalline. That's just because it's just a small water box that gets put over this whole thing. Then typically we want to add ions for one reason, because we want to have the system neutral. So typically we use periodic boundary conditions in these simulations. We cannot have a system with a net charge, because that would simply explode unless we do some tricks. And also for typical proteins, we will want to have some physiological ion concentration. And this is what the GMX GAN ion tool then does for us. For GAN ion, as an input, we also need a TPR file. This is a bit, it's a bit not that nice, but at least this is a file that we will need later as well. So we're just going to produce a TPR file as input for our ion generating tool. So GMX GROMP. GROMP is the main GROMACS preprocessor. Wait. So to be able to do that, we're going to need MD parameter files. I don't know whether you have, these should be in the repository. If you cannot do that now, then we can download that later. This is just a file that defines what the main GROMACS simulation engine should do with your system. Do energy minimization or do MD or whatever. So we're going to give it our water box with water, of course the topology file, and we're going to just say output file GAN ion.tpr. We just need that for GAN ion, for nothing else. And then we can add the ions with, let's do that here, GMX GAN ion, give it the TPR file. Let's call it ions.pdb. We give it, again, the topology file, because that's going to be modified again with ions. And we say we want a neutral box now, and we want to add 150 millimolar of salt concentration. we have to select a group of solvent because some of the solvent molecules will be replaced just randomly by ions, and we're going to pick the Sol group here. Here we also see that 16 sodium and 12 chloride ions were replaced, and these are the indices of the water molecules. And now we can also quickly look at. So now we see that we have ions added to our system. And then we are nearly done. One thing that remains to be done is a proper energy minimization. So this is a step that you always need, and sometimes even you have to think carefully about how you do it, because often after doing the setup that we just did, you will have atoms that are very near to each other, or that could potentially even overlap. And if you would just start a normal MD simulation from that, then you will get, in the first step, you will get enormous forces, and this will potentially kick out a water or an ion completely out of the box, and then the whole simulation will crash. So typically, minimization. Here we have this em.mdp file, which defines our energy minimization. We can quickly look at that. There's not much in here. So it simply says use the steepest descent energy minimization routine, do 50,000 steps, or stop if the maximum force is 250 kilojoule per mole per nanometer. And if that's smaller than that, then we consider it also energy minimized. So this simply puts a cap on the maximum forces that we're going to have in the first step of our regular MD.
Sorry?
Yeah.
If you have a protein downloaded from the PDB, you want to stick closely to the crystal structure probably. Do you would then recommend to apply something like position restraints or minimization?
Yeah.
Also to...
Yeah. You can do that, and for that we have this post-array ITP file, and then you could simply say, okay, define position restraints, and for the first minimization you would simply keep the protein untouched. That depends a bit on, it's of course it's best practice to do it like that. That's true. Yeah. Mm-hmm. And we just call it em.tpr. And then we can call now we have a TPR file. The TPR file is the main simulation binary file for GROMACS. So if you have a TPR file, then GROMACS knows what to do with it. Everything what it needs for the simulation is stored in the TPR file. And now we can simply call gmx md_run, pass it the TPR file, TPR, and for example, with verbose, I can get a little bit more information. Now we see the steps of the energy minimization. We see how large the largest force is during that phase. And here, I think we defined a cutoff of 250. So here it's first below 250, 235. So it stops here and it doesn't go on with the 50,000 steps. And now we get an output file. It's simply called confout. Or in this case, confout.gro. I could also have provided that here. What did I want to do? I would call it minimized for the next minimized PDB.
It's not PDB. Can replace it.
It's already there? I don't get it.
The extension.
Oh, I see. Should be able to recognize that. Okay, and by the way, if you want to know more about the set of MD parameters, there's a nice help page online. So it's on manualgromacs.org, and there's a large page with all the MD parameters. So there you also see MD integrator, steep, these two we just used, and yeah, everything you want to know. Okay. Now that we minimize the system, yeah. Okay, so the only thing that needs to be done is now to prepare input file for the minimized system, and that we again do with the GROMACS preprocessor. We are now going to take GMX gromp. We take the MDP file. We can take a quick look at that as well. We take the minimized structure. Oh, no. Yeah, I just realized that I took the wrong switch. I'm sorry. So for you guys to be able to do that, if you want to repeat that, I thought it was -O, but it was -C for the last structure of the energy minimization. So with that, we should now get the minimized.pdb file, although there's also GROMACS tools to convert between the formats. But for now, maybe it's easier like this. Okay, so now we got our minimized PDB. And that we take as an input for our real simulation. MD parameter file, minimized PDB. Of course, we need the topology file always, and a name for the MD run, so md.tpr. That's it. Maybe let's quickly take a look at this MD parameter file. Can we make that larger? Okay. So here we just define we want a leapfrog integrator. We're going to do 500,000 steps here. This is the time step length. We got output control here. NSTX out compressed. This is the output in the XTC file where we can then data look at the positions with time. And there's also options for Coulomb cutoff radius, van der Waals cutoff radius. This will be typically chosen according to the force field. So for example, 1 nanometer for amber and 1.2 nanometers for charm force fields. We're going to use particle mesh Ewald for the long range electrostatics. And these are typical PME parameters that will give you a good accuracy. And there's more options like temperature and pressure coupling. But I think we don't have the time today to go through all of those. So we now got our TPR file, md.tpr, and then we can simply call gmx md_run, give it the TPR file, and if you want to have verbosity, then this will give us a little bit of output here. And we see that, at least on my laptop, it would now take quite a bit now to finish that. But as you will run later these things on the GPU nodes, this will just going to take a few minutes to do that. And I think with that, you guys will be looking at the trajectories later. And if you're going to need help, there's very nice GROMACS documentation, manual.gromacs.org. There's tutorials on the GROMACS homepage, and there's also the GROMACS community forum. So if you have questions, then you can either look whether somebody already posted the question there. If you don't find an answer to that, simply post a question. There's lots of people like me who try to answer your questions there. And I think we should now be up to speed for the practicals, right? Unless you have questions, of course.
Okay, so in the course repository, in the exercises folder, in the day 1 folder, you will find my name, I'm Ole, and there are 2 folders prepared. One is the hands-on system.
Did you zoom in and make the text bigger?
Yeah.
Also, during the exercises, if you have any questions, just raise your hand and we'll come over.
There's a hands-on system setup folder prepared. And in this folder, you will find 2 different systems. Ubiquitin, which is kind of the starter system if you are getting into MD, and Sumo1, which is some ubiquitin modifier, I think. If you're completely new to GROMACS, I would suggest starting with a ubiquitin system. If you have a bit of experience, you can start with the Sumo1 system. It's not terribly complicated. There are just maybe 1 or 2 pitfalls that ubiquitin doesn't have. I have prepared this readme.md file. There you will find instructions again on what exactly to do to set up your system, then run the energy minimization, run an equilibration in the NVT ensemble where you keep the volume constant, run another equilibration in the NPT ensemble where you keep the pressure constant, and then run a production simulation. Again, yeah, it tells you what to do, not how to do it. You can look up the commands in your cheat sheet or use the help functions of the commands if you're not quite sure which input and output files you need. Look at the GROMACS forum, and of course we'll be around here. You can always raise your hand and ask us. For submitting jobs to the cluster, I have prepared this JobScript template file. You can just put it into the correct folders. For each system, you'll find 1 folder for each states of the simulation. So you start with the minimization, the NVT equilibration, NPT equilibration, and production simulation. You can just copy this file into each folder and submit it from there. I have also provided an MDP file for each stage. Again, there are lots of options in there, and if you later want to run simulations yourself, you'll have to do a bit of research which options you need for your force field, for the kind of simulation you want to do. For now, you can treat them as a black box. They are suitable for the kind of simulations we are doing, and they work. That's that from my side. If you're really fast because you have a lot of experience with GROMACS, I've also included some suggestions for trajectory analysis. You can also try that, but I would recommend starting with the system setup and simulation for now. All right, do you have any questions? That does not seem to be the case, then have fun and just ask us if something comes up.
Excuse me.
Yeah.
Should we make a file with our name and copy it there? And
Which?
we should copy the files from your folder and run in our folder name.
Yeah.
So again, if you have any questions, we will just walk through and you can approach us. And
I have questions.
Yeah.
So if I, let's say, want to visualize using UI, I'm trying to type in PyMol, but it's not how this works.
Yeah, so the visualization we'll do basically mainly in the second part, but if you want to pre-visualize already in the first half, I can, for example.
Place in Leuten sagen, dass sie
Is this how it works? Okay, so once you reach the MD run step, do not submit this on the login node, so the initial terminal. So you want to submit this to the queuing system. As far as I understand it, we do have some reserved GPU nodes where you can submit the simulations.
Even the energy minimizing.
Excuse me?
I mean, all the steps. We have like an interactive mode even to, I mean, run even the GROM command.
So it's only the last step, so GMX MD run. So this is the only compute intensive step. So every other step, like you can GROMP, you can Genion, whatever. Those you can just run on the login node. All right. So we're supposed to be in break for the last 12 minutes. So I think we're going to have like a short 15-minute break now, and we're going to continue in 15 minutes for those who are already done with their simulations, with the analysis, and those who have not sort of finished their simulations. We will sort of continue helping you like set those up. If you want to continue working on them now, also feel free. We're here like to support.
If you could listen for a second, it's just a quick reminder. If you use GMX MD run, so running a simulation, please do not do that on the login node, the one you're in. Always use S-badge to submit the job script, because if a lot of people run their simulations on the front end, it will get extremely slow for the other ones. So yeah, please make sure of that. Yeah. So if you get to the stage of running simulation and are not quite sure on how to submit the job script, just ask us. We'll come around. So another thing that came up is that the job script doesn't actually work in the way it is right now. In the line where it says GMX MD run, you have to add an option for how many MPI threads you start. So this option is called NT MPI. I think I can maybe
yours, you can just use the chalk.
Yeah, write it down on the blackboard, and probably give it like 4, a value of 4. So it starts 4 MPI threads.
All right, so everyone, I think we will just continue briefly. I will just show you how to actually see your results that you just ran. And for this, we will use a program called PyMol. First of all, who has used PyMol before? Okay, so around like a third. So for those of you who are new to PyMol, I will just briefly introduce the interface and show you how to actually open it in this setting. And for those who are more advanced, you can have a look at 2 files I uploaded in the folder with my name, which is the PyMol basics, where I have also just a PyMol script essentially that gives you some fancier visualization and some comments where you can basically see how to do things. And then I have also included a .py script where you can find basically also other like advanced fancy visualization styles which you can try if you're already familiar with PyMol. For those of you who are not familiar with PyMol, within this interface, if you open a new tab here, you can select this virtual desktop here, which will take you to another tab here. And there you can essentially use the terminal here to type in PyMol, and this will automatically open a PyMol window. So Carsten already demonstrated PyMol, how it looks. So this is the interface. Essentially, you will have basically your command input bar where you can type in commands. You will have here the structure which we are going to load. Here will be your objects that are loaded in the scene with different options. So you can For the beginning, maybe use this graphical interface to navigate, but for more advanced users, I would highly recommend using this command line because it's just much faster and gives you access to much more options. So just to see something in here, we can use the fetch command. So for example, we can use this the PDB code from the ubiquitin we saw before, and this will load in our ubiquitin here. And just you know how to navigate in PyMol. I also have basically here in this PyMol basics also under navigation. I've summarized how to navigate it, but essentially you can also just try it by trying that error, so moving your left mouse versus moving your right mouse and dragging, etc. If you're on the trackpad, I've also noted down the options in the script there, how to navigate when using a trackpad instead. Yeah. Okay, yeah. Okay. So essentially, here we have our protein, and we can zoom in. We have also different options of showing this. So, for example, we can show, instead of this cartoon, which we currently have, we can also show, for example, the individual residues here. And this can be just helpful for visualizing your trajectories. As this normally is also, in my opinion, pretty ugly, this normal PyMol view, you can, for example, run this styling script I just gave you, and there we have, in my opinion, a bit nicer representation of the thing here. Now, I guess what you want to do is also to make images and export them. So for making images, you usually use ray tracing. So you type in the ray command. You can follow that by a resolution, so for example 1000 by 1000, or you can just leave it and it will take the resolution from your current screen. And now it will take a bit of time of processing, and now in this style it will look like this. And with this we can then export as a PNG, for example under File, and then export image as, or we can also just type in save example.png. And now we have basically saved it to wherever we are currently in. All right, so now to reinitialize, so to delete everything, we can just type in delete all, for example, or we can reinitialize, that resets all our settings. And to load in basically your files locally, so now we have fetched from the PDB database. To use the local files, you can look at the cheat sheet, and there you find the options, which is load and then your structure file, and then on top of that you can also load your trajectory, and this will load your XTC or TRR file on top. Just to demonstrate how it will look, I will not load this complete trajectory, but I will load this sumo structure which we had before, which has now several states, and this will also appear if you load a trajectory, so you will have one frame is one state essentially, and there you can then play, or you can also use this cursor down here to play your animation, and the style is also then set basically on a frame-by-frame basis. All right. So I guess with this, you can already try to just play around with the settings, and then I guess maybe Florian will tell you about post-processing maybe your trajectory.
Right.
But feel free to right now just play around with PyMol and visualizing with the fetch command, or loading your local structure files. And then you can play around with the styles here, with the colors, or with the scripts I provided. And we will just answer questions if you have questions about it. Thanks a lot.
Okay. So who's already done with, or who has already generated their trajectories? Perfect. Oh, this is cheating, because you already know this. Okay. So do you actually benefit from pre-processing, that I'm telling you how to pre-process your trajectories? Okay, then I would say, so you can take, so Jonas made this like really beautiful notebook where he goes through all the analysis. I recommend you can take a look at that. I really recommend it. He's a wizard. And will help out the people who are less familiar with GROMACS. Very good.
Oh yes, and I guess Jonas leaves
an email address, so if you have any follow-up questions, suggestions, or other feedback, everything, you can send it to.
Yeah,
Jonas, I
So
guess.
we will answer your questions and just have a look at the materials. If you didn't get through it all, it should be everything self-explanatory. And if not, as Florian said, you can just contact me or any of us, and we will try to answer your questions as good as we can. Yeah.
Yeah. So there's actually a lot of stuff that we haven't gone through here, just because we noticed that a lot of people were sort of still struggling to implement the basics. But if you sort of do running simulations, then I recommend you just look at the sort of additional resources we provided right in the tab.
I have a question. Can we leave our laptop here, not going back, until tomorrow?
Yes, no.
Okay.
Thanks everyone for participating.
Yes, and enjoy the social hour.